Hey everyone, welcome to another deep dive video with me and Erik. This week we're looking at the allergies exercise. This exercise is an interesting one. It's going to be looking at bit shifting, at bitwise comparisons, lots of things to do with bits. We've got a few solutions again. We're starting with Clojure, looking at some C#, some JavaScript, some Ruby. We've got enum, we've got Gleam. We end with a recursive version, interestingly enough, in Erlang. So quite the tour we're going to go on. If you've not solved the exercise, you can solve it on Exercism. The idea of the exercise is that you get a number, a score, which contains information about all of the allergies that someone might have. And then you have to work out which allergies are actually present in that number. So we're going to be starting off by taking a look at the first exercise, which is Clojure. So we're going to dig a bit more into bitwise and bit numbers in the coming exercises, but this is a nice concise one that starts off very readable. Talk us through this one.
Yeah, I'm great that we have a Clojure solution because it's a fantastic language. The key thing here is bits, but we're going to talk about that later on. But for now, you can look at the allergies function. It starts with cont and then an arrow to the right, and then the square brackets. And the square brackets say it's an empty vector. We don't need to consider ourselves what that is. It's just a collection. And that's the thing that we need to return, a collection of allergies. Then you see a whole series of lines that look very similar. And they all call the same function. You can basically see that as a series of if statements. So if that first bit between the parentheses is bit test S0, and that's basically testing if the score is a score for the X allergen. So I'm going to discuss later on what that means. But if it is, then we're going to add X to the vector. And then on, so on, so on. So for the second bit test with 1, we add peanuts, etc., until we've had all the allergens. So it's just a series of boolean checks, if statements, and then we're going to add something to the vector once that if statement is true. It's slightly different syntax, but that's the gist of it. And then for the allergic to function, that is the function that takes in the score and the allergen. Basically, it's reusing what we've already done with the allergies function. So the allergies function returns a collection, and we're using sum, which says, is there a value in that collection? And we're using that hashtag curly braces syntax to create to wrap the value in a nice way so that you can figure out whether or not it's in that collection. And then it will return a boolean whether or not it's in that collection. So the logic is all in one single location. It's in the allergies function, and then allergic to reuses the function.
So we're going to see like two fundamental approaches to the exercise as we look through these. This one where we start with the allergies, so we make the list and then check whether something's in them. But then we're also going to see other ones in a minute where that idea is reversed and we check whether something's in there and then build the list from there. So this is a nice simple one, very readable to start with. We said that we're going to look at this bit test 0, 1, 2, 3, 4, 5, 6, 7. So let's look at that a little bit in here, Erik. This is your C# one, and we'll go into the details of the solution in a minute. But you put together a couple of different versions for us to look at. So this one is the different allergens represented by decimal numbers. So 1, 2, 4, 8, 16, 32, 64, 128. And when you're solving the exercise, this is how the allergens are shown to you. But the key thing here is that they can also be represented like this, which is in a binary format instead. And do you want to just explain what each of these numbers are, Erik?
Yeah, so if you look at those lists of numbers at the previous page, you had like 1, 2, 4. You'll probably notice that they're all multiples of 2. So you start with 1, you multiply that by 2, you get 2. Then you get 4, 8. And that actually corresponds to how you would define numbers in a binary system. So the binary number 2 is the one where the second bit is set. The binary number 1 is the one where the last, basically you're going from right to left. So let's start with that. So eggs is binary with just the rightmost bit set to 1. And that rightmost bit has either a 1 or a 0. And if it is the 1, it corresponds to the value 1. And if it's a 0, it's 0. And then the binary system works as follows, that the bit next to the left of that is the bit for the 2. So that's 2 to the power 1. And 1 is 2 to the power 0. So you can sort of start seeing the pattern. So a 1 in that position means that it's a 2. If there's a 0, it's of course, it counts for 0. And then you go further along. So you have 2 to the power 2, which is 4. So the third bit, that is the shellfish one, has the 1 at the third position from the right. And then you go on and on and on. And that means that you can see it has this diagonal pattern where the bit that is being set for that specific allergen is each time 1 position to the left until you reach cats, and then it is the very first position in a byte. So a byte is 8 bits. So the leftmost bit in a byte.
And of course, just to make it super clear for everyone, binary can, of course, represent all of the numbers. So if we wanted to have the number 3, we could just set both of these to be 1.
Yep.
But one of the nice things about the way this works in binary is you can just follow this diagonal pattern, which means then if you take a number, you can work out all of the different things that are contained in it, which is what this
and so
this exercise is trying to do.
Yeah, that's a key thing that you're now hitting on, is the fact that these bits are all in different positions. So they don't overlap. And that means that if something is combined, if it has multiple bits, you can still figure out what that bit belongs to, because it can only belong to a single one of those values. As there is no overlap, that means you can efficiently check if a value is set, basically. So that is a key part, and that's very well illustrated by these bits.
And if we go back then to the Clojure solution, you can start to see the bit test in this list here, which is basically saying, is this bit set on or off as you go through those numbers from right to left? And it's presumably indexing this one as the 0 bit, this one as the 1, this one's 2.
Or you could see it as 2 to the power 0, which is 1, or so whatever you prefer.
Yeah. So you can see here chocolate we're bit testing for number 5, and chocolate here, if we say 0, 1, 2, 3, 4, 5, we can see the 5th bit is on. And then there's another way as well, which we can use to define this, which is sort of like a bit of a shorthand syntax, but is useful for us to see because it will come up later. And that's to use bit shifting, Erik. Do you want to explain what's going on here?
Yeah, so bit shifting is basically what you were seeing, where each bit was shifted 1 position to the left. That is bit shifting. So if you start out with the very first item, it has the 1 on the rightmost position, and if you bit shift it once to the left, it means that 1 is moving to the left, and where it previously was is now a 0. But you can bit shift multiple places. So if you bit shift to the left 7 times, you get 6 zeros, and then you get a 1 looking from the right. So bit shifting is basically a way of moving bits within a number. And as we're starting out with a 1, so the number 1 for the very first value, it can just be a 1. So we don't bit shift to we could have omitted that shift to the left with 0. It basically is not doing anything. So we're moving it 0 places to the left, which is of course the same value. But then we're moving it 1 place to the left, so 1 becomes a 2. 2 places to the left means 1 becomes a 4, and so on and so on. So that is bit shifting.
Nice. And we'll see as we look through these, all 3 of these different sort of mental models for how numbers can be represented, used. But the key thing to understand, I think, as much as how this works internally, is that these numbers are the same. The number 128 is the same as this. They're just being written in two different representations. One is a base 10 representation, which looks like this, where each of these digits is worth up to 10, and this one's in a base 2 notation, where each of these is worth either 0 or 1. Cool. So let's just take a look at this code, Erik. This is your solution in C#. Tell us what's going on here.
Yeah. So you start out with the enum without having any of the values. So that's added later on. But normally an enum is a fixed collection, so you can only choose one of the values that is there, and you have to choose one of the values that is there. So, but only one. But that's not what we want, because we want the encoding to potentially have multiple of those values. And that's why it is annotated with the square bracket flags. And a flags enum, it can have multiple values. So it could have and eggs and tomatoes. But the key aspect that allows it to be efficient is that these flags should usually they shouldn't overlap. You can define flags that have overlap, for example, an all value or something like that. But now that they don't overlap, it means that every single value can be represented by combining them. And then within the code itself, so allergic to takes in an allergen, so that's one of the enum values. We first have to convert the code, which is an integer, to an allergen. So we do that by casting. So that's the C# way to convert an integer into its enum value. And then because it's a flag enum, it has a hasFlag method. And then we can pass in the allergen, and it will return true or false, whether or not that mask matches, or whether or not that bit is set.
And then you combine the list from there.
Yeah, that's a little bit of higher order functions. So we're getting all the allergen values, and we're filtering the ones where they're allergic to. So list calls allergic to now, and then making it into an array.
Yeah, so this is the inverse of what we saw a minute ago, where we were looking at the Clojure one, and you make this first and then check. In this one, you're building your checking function and then creating your list through those checks. Cool. Nice and straightforward. So moving on then into Ruby. Ruby is the first one where we are seeing two different things, I guess. We're seeing this dictionary being set rather than natural enum, and then also this ampersand.
Yeah. So this is probably the most common solution that you see, where people are making a mapping of the allergen value, which is usually a string, to a number. So that's the score, and those are again the powers of 2. So probably could have been written in a binary notation or another notation here too. I'm not entirely sure what Ruby allows, but it does correspond to the same values. So you have the mapping defined in one place only, so that's always a good thing. But then we now don't have a function like the bit test or that has flags that we had previously. So we have to do this manually. And there is a trick that you can use to see if a number has a specific bit set. And that is by doing a bitwise AND. And this is probably easiest explained if you maybe go back to that C# version with the binary notation. So if you do a bitwise AND, so take in the top 2 values. So the one with those two. If you do a bitwise AND, the result is basically comparing the bits that are in the same position. And if both bits are a 1, the result is a 1. And in any other case, it's a 0. So this means that if we would combine these top 2 values, if we compare the rightmost bit, so the topmost one is a 1, the bottom one is a 0. So they're not both 1, which means that the end result is a 0. And the same goes for the other bits. Nowhere does it have 2 1s, which means that the end result of ANDing those 2 values is a binary number with all zeros, so 0. If, though, there is a position where that those bits combine, the end result will never be 0, because, of course, it will have at least one bit, not 0. So if you go back to the Ruby code, you can see that that is why we check for not is 0. So we're getting the score of the allergen from the hash, and we're ending it, ending the score with that value, and the result of that is a new number. So this isn't modifying the numbers that are passed in. It's a new number that is being returned, where the bit positions are all set according to the logic of what I just said, where it's only a 1 when both bits at the same position are a 1. So
Nice.
if, in fact, we're only actually really checking a single bit position, because that is how our allergens are defined. So, but if the result isn't 0, then it's fine. We could also have actually written this slightly differently. So instead of doing if not equals to 0, we could have done equals and then allergen value, because it only has a single bit. So that will be absolutely the same thing here. But most people write it this way, I guess because you don't have that additional lookup being done. But you could have done this in this way, but I don't see any people do it actually.
No. Yeah, it just would make the line longer for not much
Yeah.
value. You could, of course, also have just done greater than 0 as well.
I've seen that a couple of times. Yeah.
Yeah.
Yep.
Save yourself one character.
Yeah.
And then again, so we're building this allergic to function, and then we're building the
Yeah.
list out very simply.
Yeah.
This is basically the same as the C# one, isn't it? We just filter through and check whether each allergen is allergic to.
Yeah, we're only having to iterate over the keys of that hash, of that the mapping, instead of having a function to get them for us.
Do you see many solutions, Erik, where I'm just thinking this could have been just an array, and then we could have just pulled these out? Do we have one of those coming up later?
The next one.
There we go. I just looked at this and I thought feels, thinking of what we've just seen, where each of these are sequential in this bitwise world, or in this binary representation world. It feels very wasteful. So looking then at this JavaScript solution here.
Yeah.
So we're defining an array here of all of the things. I won't keep scrolling that wide, but we can see each of these different ones, and then I guess we use that further down, do we?
Yeah, we do. So, of course, the order of the allergies is now very important, but because the fact that we're going to use is that the position in the index is the number of times we need to shift left. So for eggs, which is the very first allergen, and it only had that rightmost bit set, and then we shifted it 0 times. So that was that was the C# version where you had all the shifts. So that's that one. So you can see eggs is the one shifted 0 times. Peanuts is one shifted 1 time. So if we get the elements in the index in the right order, of course, that is being done here, then we can say in the list function on line 26, we can do filter. And filter has, it starts with the thingy between the parentheses with an underscore comma I. That I is the index. We're not actually interested in the actual allergen here. So we're doing the filtering, and then index is 0 for the very first element, 1 for the second, etc., etc. So then we are creating a new number by doing 1 shifted to the left, the index times, so 0, 1, etc. And we're doing the bitwise and. We don't use not as 0 then, because not a 0 is truthy. So if it was a 0, it will be false because it's falsy. If it is a 1, it's truthy. So that's just how JavaScript has truthiness. And
nice.
So we're doing the same thing basically, but we're using the fact that we can only define the actual allergens, and then they're using their index in that array.
So so what I was thinking when I read the Ruby one was a mixture of these, where you build this dictionary up, but you build it up by bit shifting on the index as you go, rather than manually defining all of those things.
That could also be done.
Yeah, I might play with that. And then again, very similar. We just get a list out and then check and include at the bottom for that.
I was pleasantly surprised how few people had code duplication here. Almost everybody used the other function. Kudos to everybody submitting this solution.
Yeah. Okay, so next we have nim. We featured nim a few times in the series so far. It's a language we like. So we've got an enum again. I'll just scroll to the right here with all of these different things in. And then very concise, this one, Erik. Only 9 lines in total.
I know. So nim is it's akin to the C# version, where we have an enum with all the allowed values. We don't have to set those bits. And that's the thing that makes this very elegant too. So on line 6, we are casting the integer value, so the score, to a set of allergens. And that set is actually a bit set. So it will automatically determine that if the rightmost bit is set, so bit 0, that means that the very first element in the enum, which is x, will be set. And then so on and so on and so on. So this is basically doing that whole for loop and then checking if the bit is set in a single go. And it's just, you get that by default with nim. And then for the allergic to function, you can use the in keyword, which says if does a value is a value in another list, in a set or another collection, basically. But in this case, it's a set. So this is incredibly elegant, but it does depend on the fact that if you cast to a set, it will be a bit set and it will automatically set those values correctly, depending on the bits that are set from the thing that you were casting from.
Yeah. Nice. Really good. That's a really nice one.
Yeah, love that.
Yeah, once you understand what this is doing, it's incredibly elegant and easy to read. Okay, moving on to Python. This sort of is all the things we've seen before, but structured slightly differently, Erik.
Yeah, so we have the whole list of allergens defined as an array or a list. And then there's a for comprehension. It's a list comprehension where you are both mapping and filtering at the same time. So at its core, that's what you're now highlighting. So that's the range loop. So that's going from the very first index to the last index. And then the next thing that is executed is the thing that is to the right. So that's the if condition. So again, we're bit shifting. Python also has truthiness, same as JavaScript does. So we're saying if that bit is set in the score, then we have to move to the left again. Then the thing that we return is the allergen at that index. So that is the string value. And then we store that in an allergies field. But the thing is, this is being done in the constructor, in the initialization phase. So this means that if you create an instance of that allergies class, the calculation for the allergies will only be done once. Whereas all the other solutions that we looked at will keep on redoing that whole bitwise thingy every single time. And that becomes quite wasteful. So this is a more optimized version. So, and then in the actual, the list and the allergic to method, we can just use the fact that we have already pre-calculated the value. So return item in self allergies is almost nim code. Nim is actually quite inspired by Python. So you can see the link there. And then we can just return the allergies in the list.
Nice. I feel like, I don't know Python very well, but it feels like they should have been able to call this just list and then almost make it public and be do without this this property altogether. But I don't know if that's possible. But yeah, having it as like a public, a read-only property or field or whatever, would make this even more concise.
In principle, you also didn't need to use self.allergens, I think. It could just have been a variable.
Yeah.
Didn't have to be added to the class, but still a good idea of only calculating this once in the constructor.
Yeah. Nice. Very cool. Moving on to a language that we're all fans of here at Exercism, and just a shout out as well for Gleam. It's just hit its version 1 release 2-3 days ago. We got a shiny new logo called Lucy. that comes with this version. So congratulations to the Gleam team. We've had them here on Exercism pretty much since the language first started, or very early anyway. So yeah, good for them. So yeah, talk us through his Gleam code here, Erik.
Yeah, so Gleam has also a type definition for the allergen. So that's an exclusive list, so it can only be one of those values. But you can't really assign a value to one of these cases within the type. So you have to do something else. And because Gleam is a very functional language, you have to do pattern matching. So pattern matching is the thing what we're doing here. So you have to convert the allergen to the score. And previously we could use the bitwise shifting trick, or you could assign values to the enums. We can't do that here. So it's just a simple case statement where there is a mapping from a value, a case, and then to a value. So you have to do a little bit more work. And this is a very functional thing where you're sort of separating the data type from functionality, and there's nothing a lot of you have to do functions to convert things between each other instead of having sort of types and values mixed.
Yeah.
And then the rest of the code is just standard. So you have bitwise.and. There's not a special operator here, so that's different from most other languages. And then comparing it to not equals 0. And then for the list function is basically creating the entire list and then filtering it to the ones that the person is allergic to.
Nice. So I guess it would be really nice if we could just call like allergen.all here or something, rather than having to have this whole list. Maybe the Gleam team, this little
it might actually be possible. I don't know, but
yeah, of course,
I'm not entirely sure.
But nice. Yeah, and this works again this way of constructing the list off the function as well, just to be clear. You have to keep flipping that mental model from side to side depending on which solution you're looking at. But I like this one.
There are benefits in doing it like this, because the compiler can actually detect if you forget to list one of the allergens in that case statement. The compiler can detect that. It can warn you that you forgot about handling one of these values. And other languages have this too.
Yeah. Nice. Cool. Nice work to Fright. And then final solution, we were sort of saying beforehand, we keep on ending up with Erlang at the moment on these videos, which is maybe something that neither of us expected. But actually, I think you're really liking Erlang, aren't you, Erik?
I'm really liking Erlang now, and it's got a lot of solutions that are perfect for this series. So
nice.
You were commenting on this. This will have a lot of code duplication. I'm warning people in advance. Yeah. So don't look at the code duplication. Yeah. But let's just look at...
The first thing I said when I saw this, first thing I said was like, can we not use metaprogramming or something to do this? I felt a desperate need in my Ruby head to get rid of all of this duplication. But it is a really nice recursive solution, this one, Erik.
Yeah, and it hinges on a fact that the other solutions haven't really used yet. So the key thing where this is being shown is on line 11. So you get allergies with the score and the allergies, and that second parameter is like an accumulator value. It's the thing that we are continuously updating as we go until we've reached the end. So if you go watch our recursion video if you want to know what the accumulator value is, but it's basically the allergies that we've encountered so far, and we're just going to keep on adding to that. But the thing that I want to focus on is that when clause. So that when clause says when the score is greater or equal to 128. So you probably remember that the last value had the value of 128. But this says greater or equal to 128. So if the value is 129, is that actually then that 128 value? Well, yes. So if you have 129, in binary, there's only one way to encode that, which is to set the bit that encodes 128 and set the bit that encodes 1. So there is no alternative notation possible. So 129 is always 128 plus 1. And then 130 is 128 plus 2. So anything greater or equal to 128 will always have the the bit that encodes the 128 value set. And that is what's being used here. So it says it checks then whether or not it will continue recursing with score minus 128. So basically, we're removing 128 from the result. So removing the bit as it is. This could also have been done with a bit of bitwise magic, but this is a more straightforward version. So and you continue on and on. So then you have 64, and that's the key thing with the line where you just shown, where we prepend the value to the allergies. So we're recursing with the allergy function, and we're basically saying, hey, if this value is in the allergies, then we're gonna add cats, and then we're gonna continue with the value minus 128, and we're going to continue, and we're going to continue, and we're going to continue.
I feel like all of this code that I'm highlighting here, we could just get rid of and then just deduplicate at the end, because all of this code is doing is making sure we don't add the same value to the array twice. As far as unless I'm reading that wrong, Erik, that seems to be to me what it's doing. It feels like I think if we just got rid of that, we could just deduplicate. It would be a lot. It
is. I'm not entirely sure why they do that, but
no, it wouldn't matter for one, but the fact you have that on every single one of these really makes the solution a lot bigger. But I really like it. I really like the recursive nature of it. It seems really sensible when you think about it.
Yeah, and it has thought through what it means to have a value of 128 in binary encoding. So I quite like that. But that whole list of members is just to prevent duplicates, but I don't think that's indeed really necessary, because we're not doing that. So.
And is this tail call? Is this optimized for tail call recursion?
Yeah, because if you squint really hard, there are two things that happen at the end. So it's that call, which is just a function call, nothing happens after it. And that line above is also a function call with nothing happening after it. So this is fully tail call recursive.
And if you don't know what we're talking about, go watch our recursion video, because we talk about that in a lot more depth in that previous version. Well, I feel like really inspired to go and have another go at this myself. I think I'm going to try a recursive version of this. Maybe throw a little bit of meta programming in with it. I think that's a fun thing to do. That's the last of our solutions. That's been a fun tour through some different ways people approach this. It's a pretty straightforward exercise, but as with all of them, there's a lot of different subtleties and things that you can pick out to do them. Any final words you want to say about any of the Bitwise stuff or anything else, Erik?
No, just that we have more exercises coming where we'll be using Bitwise operations. And if you've not done this, because in many languages you often don't use this because it's somewhat low level ish, but it can be incredibly fun, and it can also be incredibly rewarding if you see how fast these Bitwise operations are. So we're going to show later on in other exercises that doing some very, very clever Bitwise operations can greatly improve performance. So we'll get to some really weird stuff later on.
Sounds cool. All right, awesome. Thanks so much, Erik, for putting those together. Thanks everyone for watching. Please leave a comment. Tell us which ones of these you like. Link us to your solution, and definitely subscribe if you want to catch more of these videos as well. Thanks for watching. Have a great day.